Assalamu alaikum students, hope you're doing great. As you know that we have already started unit 15, that is electromagnetism. The topic for today's discussion is electromagnetic induction. Electromagnetic induction. An English scientist Michael Faraday showed the changing magnetic field can produce EMF which drive an induced current through a closed loop. So this phenomena is known as electromagnetic induction. In previous lesson we have discussed how how the magnetic field is generated around a conductor. So similarly, if the magnetic field can generate around the conductor, similarly we can also induce a current. So how we induce a current? This process can be learned and understand in this topic, and this phenomena is known as electromagnetic induction. For this, we need a closed loop in which we have a current, and we have to change the magnetic field, and by changing this magnetic field we will induce a current. So this current generated is this new way is not caused by a battery but due to the change in magnetic field through the coil. So for that purpose we have to consider a coil of a conducting wire, and we have to connect this conducting wire with the help of a galvanometer as shown in the figure that is shown in the next slide. When the magnet is stationary, even in the coil, we notice that the galvanometer will show no current. As we know that the purpose of galvanometer is to detect the current. But when the magnet is stationary, the magnet is not moving, we will show no amount of current on the meter that is known as a galvanometer. But when we move the magnet, either we move the magnet towards the coil or we move the magnets away from the coil, we notice that there is some deflection on the galvanometer. So this deflection basically verified that there is some presence of current, and this current is basically a induced current in this circuit. So if you see the figure A, at the very top there is a galvanometer. Then we have connect any loop to this galvanometer, and there's a bar magnet. So when we move the magnet towards the coil, we notice that there's a line that are shown in the figure. These lines basically, when these lines pass from the loops, they induce the amount of current, and we see the needle will be at the 10. Similarly, if we see the figure B, in figure B we are not moving the magnet. Magnet is stationary. So when the magnet is stationary, the galvanometer show no reading. It is at 0. It's mean when magnet is stationary, the current will not induce. Similarly, we see the figure C, we are moving the magnet away from the coil. Even moving the magnet away from the coil, it shows some deflection that is at minus 10, right? So by moving the magnet, the current will be induced in the circuit, and if the magnet is placed stationary, then current will not be induced. It should be noted that when the magnet and coils are moved toward each other, galvanometers show deflection in one direction, right? So basically the two different directions are shown when we are moving the magnet towards the coil and when we are moving the magnet away from the coil, right? Similarly, these kinds of effect can be observed when one coil is connected to the battery of a power supply. Then we call this coil as a primary coil, and if while the other coil that is connected to a galvanometer in a closed loop is known as a secondary coil. When the primary coil is moved towards secondary coil, the galvanometer show a deflection that indicate there is a presence of an electric current, and that electric current is basically a induced current in the secondary coil, and this induced current is produced basically by the changing magnetic field in a primary coil. When the primary coil is moving away from the galvanometer, this time we showed that there is a deflection, but the direction of deflection is opposite. When the primary coil is held stationary, means it is not moving, and the secondary coil is moved, the same effect will be observed. So again we will observe the relative motion but between the two coils that induce the electric current. If both the coils are held stationary but supplied current in the primary coil is changing magnetic field, it produces changes and an EMF is induced in the secondary coil. So basically all this process is the working principle of a transformer that we will learn in the next few topics. So there are some factors that are affecting magnitude of induced EMF. The very first factor is strength of magnet. The greater the magnitude of magnetic field, the greater will be induced current. So it depends upon the if we provide the large magnitude of magnetic field, the large amount of induced current will we get. But if the magnitude of magnetic field is less or small, then the induced current will also be small. The second very important factor is the length of a conductor. It can also be shown that if the longer the length of the conductor, the magnetic field, then the greater the induced EMF will be. The speed with which coil or magnet is moving. The faster the wire is moved, the deflection on the galvanometer will be more faster. This indicates that the speed at which the conductor through the magnet field also determine the magnitude of an induced EMF. The last factor is number of turns in the coil. When a double loop of wire is used, the deflection galvanometer is twice as large as before. And if we increase a loop to a triple time, it will induce three times the more EMF and so on. So it depends upon the number of turns as well. If we increase the number of turns in the coil, the induced EMF will be more, and if we decrease the number of turns, the induced EMF will be less. So it means the EMF is proportional to the number of turns in a coil. So, direction of induced EMF and conservation of energy. The direction of induced EMF and induced current is in a closed circuit is such as to always oppose change in magnetic flux. So, magnetic flux is basically the strength of a magnetic field in a loop. It depends upon how many magnetic lines are passing through a certain surface area is known as the magnetic flux. The induced current around a loop produces its own induced magnetic field. This field we compared with the external magnetic field of a bar magnet cannot prevent the magnet through the loop from changing, but its direction is always such that it tries to prevent from the changing. So if you see the figure, consider the pushing the bar magnet, the not fall into the loop, it causes the induced magnetic field to increase of the bar magnet in the upward direction. If you see the figure A, that is labeled as not fall push into the loop. To oppose the change, the loop itself needs to generate the induced magnetic field that is acting at the center of the loop, and it is pointing downward. As a magnet which has a north pole at the bottom which repels the north pole of the bar magnet, as we know that when we bring same pole together means we know that like poles they repel each other. The moving towards the loop using the right hand rule only if the induced current is counterclockwise as seen from below a face north of bar magnet that is shown in figure 15.11. If you see the figure A, the north pole push it into the loop, the current will be induced. And if you see the figure B, the north pole push out of the loop, again here the current and EMF is also induced in this case. If you see the figure C, when the south pole is pushed into the loop, the red circle line is basically the loop in which the uh, south part of the magnet is pushing inward. So this will also cause to produce a induced current and result in induced EMF. Similarly, if we see the figure D, the south pole push out of the loop as well. So these are the effects that are observed with the south pole of the magnet that is pushed in and out of the loop. And it is seen that induced current set up as an induced magnetic field of its own. From all this figure, it is clear that the motion of magnet is always opposed by the magnetic field generation from the induced current. So the mechanical energy that is spent is basically in the opposite direction is converted into electrical energy. If the induced current were in the opposite direction, the magnetic force would have accelerated it with no external energy source. This would have been a clear violation of a law of conservation of energy which does not happen in the nature. So this is all about the today lesson. Hope you understand this. If there is any confusion, we will discuss in the school. Thank you and Allah Hafiz.